Hello and welcome. In this video, we're going to talk about the voltmeter loading effects. So voltmeters are usually placed in parallel with the resistance we want to measure across. And we see that here, the positive side is on top of our R3 and the negative side is on the bottom of our R3. And we're going to get VR3 out of this. The internal resistance of our meter, the RM, we want to call it that for our resistance of the meter, will be placed in parallel. And we see that in this next one here, where we replace the meter itself with a resistance, and we call it RM, the meter's internal resistance. And if that meter's internal resistance is too close to the resistance value of R3, then we're going to have a problem with the potential being shared. It's going to affect how it's measuring the circuit. And so we'll see that as a parallel combination over here. We see that it's R3 in parallel with the meter's resistance. So if we were to measure this, we would have to take that into account if our R3 is anywhere as close to our RM value. So in this case, we have an R1 in series with R2, and that would be put in parallel with the R3 and the meter resistance. So we're going to do a couple of these to see how exactly this is going to affect the voltage that we're measuring. In this example, it says, how much does the digital voltmeter affect the voltage being measured in the circuit if the meter's resistance is 10 mega ohms? So 10 million ohms. And we'll see that the 15 volt source here comes down through R1. So R1 is in series. When we do our RT, we'll say that it's R1 in series with, we hit a node, so we'll open a parenthesis, and we'll place R2 in parallel with our meter resistance. R2 parallel to RM. And that will be our total resistance equation. From there, we can actually do our voltage divider equation. We can say that the voltage across R2 will equal, and that's going to be what this meter actually reads here. That's going to be our total resistance on bottom divided by what we want to know the voltage drop across, and that's going to be both of these parallels because the voltage is shared at the node. So we want to find that voltage at the node location there. So we'll put R2 in parallel with RM on top, and we'll multiply that entire thing by our voltage source. And we got that 15 volts at the top there. So let's calculate this out, and we'll compare it to ones that increase, because the next two have an increased resistance. And we'll see that this is going to affect how they respond. So we know that this first one is going to be the parallel, so we'll do the parallel here. 1 over. Our R2 value is 100. We'll place 100 there. We'll say plus 1 over our meter value of 10 million, so 10 times 10 to the million, that's positive 6. And we're given a 99.999, right? That's really, really close to our smallest resistor. And that's because these two are so different, right? 100 and 10 million have a big difference in between them, which means that our parallel combination is going to be really, really close to the smallest resistance value. And that's what we want. That's going to be the least impactful on our circuit. It's going to read the truest for us. So that is our two parallel there. So we can take that value and add it to our R1 value. That's going to be our total resistance. We know that that's 180. Plug that in. So now we're given 279.999, or 280 just about. We'll do our voltage drop equation here. We'll say that we have our parallel on top, that's at 99.999, divided by our total resistance. We can put our answer in for that. And we'll close that off and multiply that by our voltage source of 15 volts. So we expect that meter on the first circuit here to read 5.36 volts. And when we change up our resistor values, the R1 becomes 180 kilo ohms and R2 becomes 100 kilo ohms. We can replace that in here. We can say that instead of just 100 right here, we're going to say times 10 to the positive 3. That's going to increase this. Look at that. Now we're down already 1,000 from our main value there. We expected that to be really, really close to our R2 value, and it's 1,000 below at least. And so now we can add that to our 180 times 10 to the positive 3. And that's going to get us up to our total parallel resistance here. So we can replace our parallel combo. We got our voltage divider set up here now. And now we got a 5.322, just 5.32. And that's what our voltmeter would read now that this resistance is closer to the meter's resistance. So we got to watch out for that. We don't want that meter to get too much of the voltage, because when the meter has voltage drop across it, it's going to have current through it, and that's going to fault that meter. So let's do one more here. The next one has a 1.8 mega ohm and a 1 mega ohm, and our meter resistance is still going to be 10 mega ohms. And so now we're getting really close to that meter's resistance, its internal resistance. So we're going to increase this one up here. We're going to say that it is a 1 mega ohm. So we'll do +6 there. And this one is also going to be a 1.8 mega ohm. +6 there. So we'll place in the parallel combination on top of our voltage divider equation down here. And we're getting a 5.03 now. So our meter would read 5.03 volts. Right, so now our measurement of voltage across this resistor is no longer accurate. We're actually dropping some voltage across our meter, some voltage across our resistor. We're not getting an accurate reading for that. All right, let us know if you have any questions.